Morning. Okay, so we're well into automata now, into finite state machines, and we've done both deterministic finite state machines and also non-deterministic finite state machines. Next up, what we're going to do is try to describe in some systematic way the collections, the languages, collections of strings that are defined by a particular finite state machine. So that is to say, if you write down a finite state machine, just say a deterministic finite state machine for starters, if you write down a finite state machine and you look at which strings will be accepted, will be recognized by that finite state machine, what's the language? Can you write down what the language is in some reasonable way? And the answer, of course, is yes, because we're going to do it today. Because you can express what the finite state machine describes using what are called regular expressions. So regular expressions are a very compact, very powerful language, a very compact, very powerful way to describe what it is that a finite state machine recognizes, accepts, the language. Okay, so here we go. Okay, so there's a pattern to the languages that are accepted by a finite state machine. And we can describe such languages with regular expressions. So this is one of those cases where you really want to do examples first and then a definition. So let's see. Oops, did I go two? Oops. There we go. So there we go. Okay, so for example, a regular expression is going to be a string, and it's going to involve here some characters from the underlying. Here's the string, in case you can't tell. It's going to involve some characters from the underlying alphabet here, characters like H, A, E, I, O, U, T. So I'm imagining that this particular regular expression involves characters that are from lowercase ASCII letters. And what you see is that there's an H at the beginning, a T at the end, and then in parentheses are the traditional vowels. So this is a compact way of describing what in English you might say, start with an H, end with a T, put a vowel in the middle. This regular expression describes the language consisting of 5 words of 3 letters each. So the 5 words are hat, het, hit, is het, anyway, hot and hut. So this regular expression describes this language. Regular expressions are a way to describe languages. Now, of course, you see that there's this pipe operator here, pipe, and that's a kind of an or. And there are parentheses, which kind of do a certain amount of grouping here. So we're trying to say that the vowels are all grouped together. So those are not going to appear in the language. Those are not going to appear strings that appear in the language. Instead, those are meta characters. They are used to describe things, and in the regular expression, they form grouping or ors, alternation. Okay, besides the pipe operator and the parentheses, regular expressions also use concatenation because the initial H is concatenated with a vowel, and that in turn is concatenated with a T. So the concatenation is kind of silent there. We didn't explicitly write concatenation, but nonetheless it's there. Okay, so regular expressions involve somehow characters from the underlying alphabet, the alphabet that is the string alphabet of the finite state machine, and you're allowed in the regular expression to do things like grouping with parentheses, alternation with the pipe operator, and concatenation just by abutting. So another example illustrating the kind of most interesting thing that you can do. The regular expression A, B star C, and again I'm underlining it just so that a person is sure what I'm talking about, that's a regular expression. The regular expression A, B star C describes a language, of course that's what regular expressions do, whose words begin with an A, followed by any number of B's, and the part that sometimes snags a person is possibly 0 many B's. So it's an A followed by any number of B's, a repetition of B's, and an ending with a C. So again, you see the concatenation, but what's new here is the star operator. Star means any number, including possibly 0 many. So one of any number is possibly 0 many. And that regular expression, as all regular expressions do, describes a language, and here's the language. It's the strings A, C, where'd the B go? And the answer is, well, that's 0 many B's. A, B, C. A, B, B, C, etc. So there are infinitely many strings in this language, infinitely many strings that are described by this single regular expression. And so the regular expression gives a very compact way to describe this language. And of course, we're thinking that there's a finite state machine that accepts strings matching that pattern. Here's a machine here, a standard looking kind of deterministic finite state machine. And do you notice that the middle state there, Q1, is a double circle state, is an accepting state, and Q2 is not. So the example simply is, if you ask yourself which strings are accepted by this machine, why, you can have some number of A's, so with that we're going to need that star operator. You can have some number of A's followed by a single B followed by some number of A's. And when I say some number of A's, I could mean zero many A's, because you could just go straight in with the B. So I'm associating this regular expression with this machine. Those two are associated in the sense that they both describe the same language. They both are a way of defining the same language, the language accepted by that machine. The language recognized by that machine, language of strings accepted, I should say, by that machine. Okay, so what do regular expressions look like? And the answer is regular expressions follow this grammar. This grammar doesn't say anything that we didn't say on the prior slide. All we're trying to say is that you can make a regular expression using the vertical bar. You can make a regular expression by concatenating things together. You can make a regular expression by using the star operator. And you can make a regular expression by having a beginning, an open paren, and an ending closed paren, and then you're allowed to use characters that are in the alphabet sigma. Okay. There's a little bit of technical jargon here that's a kind of, sigma can't contain a closed paren, because otherwise you'd confuse it with the closed paren that is the meta character, or an open paren, or a pipe character, or a star. I mean, that's just bookkeeping nonsense. So what's happening here is that you're allowed to make regular expressions following the rules that the examples on the prior slide show you. Can I make those rules mathematically precise? Well, I did. I just did. That's exactly what we're looking at. Once you write down what the rules are, you of course have to say what they mean. I mean, you couldn't go into a programming class and the first day the instructor hands you, 5 or 6 pieces of paper, say this is the rules of the C language, start programming. Of course, you have to understand what those rules mean. So we have to describe what the rules mean. One of the things you might see from the prior page is that did you notice there's an empty set symbol here, and there's also an empty string symbol here? Okay, so we got to describe what does it mean when a regular expression contains an empty set symbol? What does it mean when a regular expression contains an empty string symbol? Okay, so that's in the first paragraph. If your regular expression contains an empty set symbol, why then the associated language is the empty language. The empty set, the language of course is a set, so the empty language. On the other hand, if the language contains the character empty string here, then what you've got is not an empty set language. What you've got is a one-element language consisting only of the empty string. So it's easy to confuse the empty set with the set containing the empty string, but they're different. The set containing the empty string has one element, namely the empty string, and of course the empty set doesn't. It has no elements, of course. Then finally, the last thing that is similar to those two is down here, is that it's possible for a regular expression to contain a single character, like lowercase a or lowercase b or 0 or 1 or any single character from the alphabet. Okay, well, if the regular expression contains a lowercase a or a lowercase b or a single character from the alphabet or whatever it is you're looking at, why then the associated language is just, whoops, I hit the wrong place. The associated language is just the set consisting of that one character. So the language of the regular expression, just an A, is the set consisting of just one string, where that string is just one character, A. Okay, and then of course you know how mathematics works. We start out by describing some kinds of baseline beginning, sort of base case steps, and then we talk about the operations that put those base case steps together. So I broke it into two paragraphs just to break it into two paragraphs. So how can you put things together? And the answer, of course, is you can use a pipe, you can use a concatenation, and you can use Kleene star. Okay, so what does pipe mean? So if you give me a regular expression R0 and R1, then suppose I pipe those two together like I did with the vowels in my very first example. Suppose I pipe them together, well, you get the union of the languages. So that's right, I ended up with HAT and HET. Union together gave me the two strings together in one set. Concatenation of the regular expressions describes concatenation of the languages. So when, for example, I had the regular expression, let's say HA, that's a two-character regular expression, why then that would describe the language of H concatenated with the language of A. Of course, the language of H consists of this single string, one character long, just an H. The language of A consists, the language of the regular expression A consists of the single string, one character long A. And when you concatenate those two languages, as you say, you concatenate all the strings they contain, you end up with one single string, two characters long, HA. And then finally, Kleene star. The Kleene star, the regular expression, describes the star of the language, which of course we described earlier. And we were careful to say earlier that if you want to write down something like AB in parentheses, A or B in parentheses, so A pipe B in parentheses, and then a star that does not consist, when we define what is the star of a language, it does not consist of pick one of the two, A or B, and then repeat it. That's not what the star of the language is. Instead, the star of the language is pick one of the two, write it down. Pick another one of the two, write it down. Pick another one, so you can end up with ABA, for example, and iterate as many times as you please, and finite times as you please. Okay, so you can't just describe the syntax. That's good, but it's not enough. You have to also describe what regular expressions mean, and this is the formal definition of what regular expressions mean, but we want to put down as many examples as, you can write down too many examples, but you can also write down too few, so it's time for more examples. Okay, so for example, if I want to write down, describe the language of strings of A's whose length is a multiple of 3, so that is to say one way that you can describe such a language here is this way, that set notation, the collection of languages, collection of strings whose length is a multiple of 3. So you might have AAA, that's when K is 1, AAA, AAA, that's when K is 2. Don't miss the K equals 0 case. That's the empty string, and etc. You see where I'm going with this. So how do you describe that language? Well, the answer is you write down the regular expression AAA, put parentheses around it with the star. And why do I need parentheses around it? Because if I just wrote A star, a person would think that meant two A's and then an A star. So you need the syntax, don't get me wrong, but you also need the semantics. Okay, next. The regular expression A star and then epsilon B. So I'm trying to describe somehow what's the point of the epsilon. So A star and then epsilon B here describes the language of strings. A star and epsilon B describes the language of strings that have any number of A's, optionally ending in 1B. So what I mean there is that you can have 0 many A's, that's A star allows 0 many A's, and then you choose to pick from among these two, you choose the epsilon. So you have 0 many A's followed by epsilon, and then taken all together, that gives you an empty string. You could have 0 many A's, and then of these two, you pick the B. So you end up with 0 many A's followed by a B. You could have 1 many A, that's the star, allows you to pick 1 many A. You could have 1 many A followed by the epsilon, the empty string, or you could have 1 many A's followed by a B. You could have too many A's followed by an epsilon, or too many A's followed by a B. So what the epsilon gives you is it allows you to say, and optionally add a B. So the epsilon may have struck you the empty. So what's the point of having the empty string? Well, the answer is it's useful. Here in this example, it allows you to say optionally add a B. Okay, so similarly, to describe the language, the collection of strings, language consisting of words with between 3 and 5 A's, so 3 A's, 4 A's, 5 A's, you can use A, and then epsilon or AA. So again, optionally pick either double A or single A, and optionally is the epsilon because you got to pick something. So if you pick the epsilon, if you pick the empty string, why then that acts as though you hadn't picked anything. Okay. To match any single character, suppose for example you want to say any lowercase letter, you can just list them all. So for example, the language consisting of 3-letter words ending in BC is written right here. I'm going to take the alphabet in this example to be sigma equals ABC. It's common to use lowercase letters like ABC for these examples because if you have zeros and ones or digits or something, you can sometimes confuse them with how many times you iterated, sort of stuff. So with the letters, it has the advantage that you don't get that confusion. But so here, the language consisting of 3-letter words ending in BC is ABC, BBC, and CBC. So if you want to say something like match any character, one option is to simply list them all. Of course, if you had all the lowercase letters, it would be annoying. If you had Unicode, then it would be basically not possible. I suppose you might write a program to write that regular expression, but in any event, it would be a bother. But we're only working with ABC, so it's not much trouble. And so you write down here A or B or C, followed by BC. Okay, so to match any single character, we can just list them all. The language of words starting with any number of A's, including 0 many A's, followed by a single B, and then ending in fewer than 3 C's. So we can actually get some pretty complicated descriptions here. So the language, I've got a B, BC, BCC, AB, ABC, ABCC, has words starting with any number of A's, possibly 0 many, followed by a single B, and then ending in fewer than 3 C's. So really the thing to watch for is that B, but in any event, to describe it, I can use any number of A's, single B, and then ending in fewer than 3 C's, and that includes 0 many C's. And I can't overemphasize how often a person gets snagged by the 0 case. It would be very common for me to say, give this as a quiz question, and a person would respond with A star B, C or CC, and forget the 0 case. I'm guilty of that myself, do it all the time. It's very easy to slip up. Okay, so more examples. I'm going to produce 4 examples here and produce a regular expression that matches each description. So I'm going to do it with pencil and paper just because this foolish marker here, what do you call it? The tablet. There we go. The tablet that I used to mark on doesn't really work all that well, especially with my handwriting. So here we go. I'm going to see if I can't work out. There we go, and down to here. Okay. One thing about these, went the wrong way. One thing about these darn things is there's this delay, but I'll do the best I can. Okay, so what am I looking at here? So for starters, I'm looking at a set of strings that ends in 3 consecutive ones. So I got to produce a regular expression for the set of strings that ends in 3 consecutive ones. All right. So I'm going to take the alphabet to be the binary characters, the bits 0 and 1. Okay, and just the 2 1-character strings 0 and 1. Okay, so I'm looking for the set of strings that end in 3 consecutive ones. So for number 1, I'm looking at. Whoops, I forgot to put my light on. There we go. I'm looking at here, say 0 or 1. So any kind of character repeated any number of times, and then it's got to end in 3 consecutive ones. Okay, so at least for the simple ones, the difference between the regular expression and the English description is not really all that large. Let's try the next. The set of strings with at least 1 0. Set of strings with at least 1 0. Okay, so set of strings with at least 1 0. So somewhere in there you got to have a 0. But before it, you could have any old junk, and after it, you can have any old junk. So I'll write it this way. Isn't the only right answer, but it's the one that I would expect to see most people would hand in. So the point is that you got to have a 0. You could have 0 many ones, that could happen, and you could have 0 many characters after, that could happen, but you got to have that 0, and that's exactly what I'm required, the set of strings with at least one 0. Okay, let's try another one. The set of strings containing at least 3 ones. Now it doesn't say they got to be consecutive, it just says at least 3 of them. So the set of strings containing at least 3 ones. So you say, well, there's got to be a 1, there's got to be a 1, and there's got to be a 1, and in between can go any other stuff. So fair enough, I'll write it this way, but there are other things that a person can do. So 0 star 1, 0 star 1, 0 star 1, and then 0 or 1 star. Okay? So I've got the 3 ones, the 1, 2, 3 ones. If you want to put stuff after that, hey, go for it. And if you want to have zeros in between, hey, that's fine too. But the point is that you got to have the 3 ones. Okay. What's question 4? I forgot already. Whoops, pop it up. What's question 4? I forgot already. The set of strings starting with a digit other than the one that it ends with. The set of strings starting with a digit other than the one that it ends with. So if it starts with a 0, it's got to end with a 1. If it starts with a 1, it's got to end with a 0. So I think there are 2 cases. So this is one of those things where because there's finitely many characters, I can just cover the 2 cases. If it starts with a 0, it's got to end with a 1. Pardon me. In between can go any stuff. And the other possibility is if it starts with a 1, it's got to end with a 0. And in between can go any stuff. Okay, so because there are finitely many possibilities, I can just write them out as cases. And again, a person can say, well, what if there were 256 possibilities? It would be annoying. Be very annoying. But you could write them out as cases, or more importantly, you could write a little script that could write them out as, maybe not importantly, more practically, you could write a little script that wrote them out as cases, but you could do it, absolutely could do it, at least in principle. It would be annoying, but in principle, you could do it. Okay, we're going to stop there for the video, just because we've done a lot and because I don't want to go on too long. Next video is a part B of the same thing, so we're going to be talking some more about regular expressions. Very good.